organizer, just as a participant who enjoys the workshop. And his reaction was, so tomorrow, with that, we are very, very happy to have Dakshita continuing the quantum session on quantum cryptography after Mark. Thank you.
Thank you. Thanks, Yael. So, hi everyone. Nice to see many of you after so long. This is going to be part one of part two of the quantum cryptography tutorial. It's going to be a little biased towards the kind of questions I find fascinating and enjoy thinking about, of course. So that's just a disclaimer. There's a lot more in quantum crypto than what I'll be able to cover. But I'm going to try to give you a taste of some of the magic of quantum and how it interacts with cryptography. Okay, so let me just first distinguish between post-quantum cryptography and quantum cryptography. Post-quantum cryptography, which you heard a fair amount about in the first part, considers cryptography where participants are classical. The honest parties only have classical capabilities, and they're trying to ensure security against a quantum adversary. And in terms of the amount of cryptographic hardness or the structure in the assumptions, this is at least as much as what you need for classical cryptography, often more, because we all saw how Shor's algorithm breaks a lot of the cryptography that is classically secure. On the other hand, quantum cryptography considers a setting where participants themselves have quantum capabilities, and they can use these capabilities in different ways to create protocols that look quite different from the classical protocols that we've been used to. And of course, here also we want security against quantum adversaries. This, on the one hand, enables new types of cryptographic capabilities just by harnessing the inherent nature of quantum information. Again, I'm going to show you some examples soon. But also, this potentially requires less hardness and less structure than classical cryptography for the very same tasks that, like secure computation, that we've been interested in for many years. Okay, so there's been a trend of reflecting back onto what was happening a few years ago. This is not from 10 years ago, but from 5 years ago, when there was a program on lattices and another program on quantum happening at the same time. And we requested some experts in quantum cryptography to teach us a little bit about both quantum and crypto. And in one of those talks, Christian Schaffner had this mind map of all the open questions and directions in quantum cryptography. And as you can see, there's a lot of them. It's probably hard to read them all. So I just wanted to put it out there. It has questions like pseudo-random unitary somewhere on it, and quantum digital signatures, how to build quantum crypto functionalities, and so on. Studying secure computation, for instance. And I would say there's been a good amount of progress on many of these questions over the past few years. Okay, so with that, in the first part of this series, we'll look at what are called Weissner encodings, first introduced by Stephen Weissner, and some simple applications, some simple ways to use them to wield the power of quantum to build crypto systems. So we'll start with the classic example of quantum key distribution, move on to oblivious transfer. We'll also talk about randomness generation, certified deletion, and quantum money. And then towards the end, I'll say a little bit about this primitive called oblivious state preparation, which I like to think of as a computational replacement for these Weissner encodings. So I'll say a little bit about it. And so let's get started. So what are Weissner encodings? These are simply these four different quantum states. The first two are computational basis states, Ket0 and Ket1. You already saw in the first tutorial, these can be represented as vectors in 1, 0, 0, 1. And the other two are these Hadamard basis states. The Ket plus is a uniform superposition of a 0 and a 1 with a positive phase between them. And Ket minus is a uniform superposition of a 0 and a 1 with a negative phase between them. Again, their corresponding vectors look like this. These encoding, these states called Weissner encodings, were first introduced by Weissner, who said that they can be used as a means for transmitting two messages, either but not both of which may be received. So as you can see, this is long ago, before OT was discovered. This was also foreshadowing OT. Okay, if you look at the density matrices of these states, which can be created by taking the ket vectors and then taking the conjugate transpose of these vectors and computing an outer product between them, what you get is the density matrix for the 0 state, for the 1 state, and similarly for the plus and minus states. And the way we represent distributions over quantum states, we will often call these mixed states, is by adding up these density matrices and placing weights against them. So if I were to sample a ket 0 state with probability 1/2 and a ket 1 state with probability 1/2, then the corresponding density matrix is 1/2 times this matrix plus 1/2 times the matrix below, represented as this red matrix on the right. Similarly, if I were to sample a plus state with probability 1/2 and a minus state with probability 1/2, the density matrix is represented here. And the cool thing about these encodings is that the two density matrices here are identical. And what this means, really, is that an experiment where I sample 0 with probability 1/2 and get 1 with probability 1/2 and give you the resulting state is actually identical in terms of like every possible measurable outcome that you'll get. This is identical to an experiment where I sample plus with probability 1/2 or a minus with probability 1/2 and give you the resulting state. Okay? And this is going to be useful. All right. Let's talk about measurements, since I just said that word a few seconds ago. So a measurement is an operation that you can perform on a state, and this is a way to recover information from that state. So if you were to take the computational basis states and perform a computational basis measurement on them, one analog of this is passing these states that have been polarized in the horizontal vertical direction through a light filter that can also detect horizontal vertical polarizations. Then you'd get, in the first case, you'd get 0. You'd see that the light passes horizontally, not vertically. In the second case, you'd see that the light passes vertically, not horizontally. Okay. On the other hand, if you took Hadamard basis states to begin with and passed them through the same computational basis filters, what you'd see is a 0 with probability 1/2 and a 1 with probability 1/2, regardless of whether you started out with the plus state or the minus state. So what this is saying is that the post-measurement state, after you did the measurement, the value you observe, as well as the state that you end up with, is going to be identical, irrespective of whether plus was being originally transmitted or get minus. Again, this is a useful feature of quantum information that we'll see ends up helping cryptographically.
This is if you measure in the standard basis, then.
This is if you measure in the standard basis. Yes, so computational basis is often also called the standard basis. If you measure 0 and 1 in the standard basis, you see 0 and 1 respectively. If you measure plus or minus, you see these probability distributions over 0 and 1. Okay? On the other hand, let's see what happens if we perform a Hadamard basis measurement. So think of this as now placing a filter that is checking for light polarized diagonally. And if you measure the 0 state in this basis, you see a 0 with probability 1/2 and a 1 with probability 1/2. Similarly, if you measure the 1 state in this basis, you see a 0 with probability 1/2 and 1 with probability 1/2. So again, regardless of which standard basis or computational basis state you started out with, you see the same output distribution. And in fact, the post-measurement state is also going to be identical. So in some ways, this is hiding information about what state you started out with. And this is going to be useful. Okay? And again, if you had Hadamard basis states to begin with, and you measured them in the Hadamard basis, then you recover perfect information about which state you started out with. So plus state measured in the Hadamard basis will give you 0, minus will give you 1. Okay, so this is fairly simple. I'm going to move on. Please interrupt and ask if you have any questions. So I'm just going to move on and tell you about the first application of these Weissner encodings. This is the classic quantum key distribution, first proposed by Bennett and Brassard. let's start out by simply trying to use these states and see if we can do anything interesting with them. So what Alice is going to do, Alice and Bob are trying to agree on a secret key. Yeah, that's the key distribution setting. And they want to make sure that no eavesdroppers learn this key. So what Alice will do is sample a bunch of bases and sample corresponding bits, and then prepare the corresponding Weisner encodings. So basis C means it's going to be a computational basis state, and 0 on X means it's going to be the 0 computational basis state. H and 1, for example, means it's going to be the minus state. Right? So she prepares all of these states and sends them over to Bob. And then later on, Bob says, okay, hey, I received the states. Now Alice can reveal her bases, her choice of bases, and Bob, by measuring his states in these bases, will obtain a string X, which, if you had ideal quantum channels, is going to be identical to the state that Alice started out with. Sorry, is going to be identical to the string X that Alice started out with. Okay? So simple stuff so far. But this is too simple. This does nothing. So far, we just sent a bunch of states, gave them the basis. We could have achieved the same thing with classically simply communicating the string X. Right? So the problem with all of this so far is that if you had an eavesdropper sitting on the channel, and if the eavesdropper had the capability to replace the states that were being sent from Alice to Bob with states of her own choice, then Alice and Bob would actually think that they share, yeah, so Alice and Bob would end up thinking that they shared a key, but what actually happens is that Alice and Eve have access to these set of states from which they can compute a shared key. So Alice thinks she has a key shared with Bob, but what she actually has is a key shared with Eve, and this is terrible. So far, not a good protocol at all. Okay. So the way to fix this is going to be to employ our favorite trick in the cryptographer's handbook. One of our favorite tricks, I guess, is cut and choose. So what we will do is, in addition to revealing the choice of bases that Alice used, she will also reveal part of her string X, some part of her string X. Now what Bob can do is measure the states he received in the bases that Alice just sent him and check whether the revealed part of Alice's string matches his string. Okay? If this check passes, so if the string Y restricted to this revealed set S is identical to X on the revealed set S, then Bob communicates to Alice that it is safe to reveal, to use the rest of the string as their shared secret key.
They could still differ on like one bit.
Yes, they could. There's errors here that we can. Okay.
So I mean, when we talk about classical, not without quantum, we care about, let's say, honest but curious. They feel like a very malicious kind of evil.
Yes.
So you're saying even if we talk about honest but curious in the quantum setting, the only way to be curious is to like measure the state.
Exactly. So if you're just observing states go by, then there's no way to do any, like you don't have the states.
It's like honest.
So then this simple protocol that we said before, if you're really honest and not touching the states at all, this is secure.
Yeah, but that's not the right honest but curious
Yes.
definition for the quantum setting.
Yes, so the right definition considers exactly an Eve who actually keeps the states with herself and is now going to use the rest of the protocol to come up with it.
Yeah, the point is
Shared
that curious in the quantum setting alters the state. That's
Yes.
kind of, it's
Yes.
like malicious in the,
Yes,
So are you also assuming authenticated classical channels?
yes, exactly. So that was the very next thing I was going to say was we're assuming that Eve cannot change this communication between Alice and Bob in the sense that they have access to an authenticated classical channel. Does that also answer you?
Because otherwise you can never, there's nothing
Yes.
between Bob and Eve.
Yes, exactly. Otherwise, there's no difference between Bob and Eve. So you need something to make sure that Bob's classical communication to Alice is actually coming from Bob. Yes.
So they're assuming that we're getting channels in both directions for X state and with the base.
Yes. It's a good question whether you could use only one direction. Never thought about it. Okay. All right. So this actually is the protocol. And now if you consider an Eve who tried to replace the states Alice was sending with some maliciously chosen states of her own, then it's more likely than not that this test is not going to pass, right? The cut and choose check is not going to pass. And like Surya was pointing out, there's still some chance that it passes. Let's say Eve replaces one of the states with something of her own. So you need to do a little bit of error correction to fix those things, but it's doable. Error correction and randomness extraction will fix these things. All right, so this is all I'm going to say about key distribution. I'm going to move on to, one last thing. Analysis of this protocol is fairly non-trivial. There's been many different analyses over the years. My favorite is in this work of Bowman and Fair, which involves a type of cut and choose theorem for EPR pairs that is pretty useful, and in fact pretty useful in the analysis of most of the protocols I'm going to tell you about in this talk. Okay. So the next one is oblivious transfer. So instead of building oblivious transfer, we're going to try to build secure erasures. So what is secure erasures? It's just going to be an erasure channel between Alice and Bob, where Alice can drop her message into this channel, and the channel deletes this message with probability 1/2 and transmits it probability 1/2 to Bob. Now, so far, this is trivially simulatable. Alice can just decide not to send it to Bob, and this is deleting it. But of course, we want some non-triviality here. We want that Alice should not know whether or not her message was transmitted to. It's important that Alice doesn't know whether the message got through or not. This is also known as generalized oblivious transfer, and you can get oblivious transfer from this, and you can get general purpose secure multi-party computation as long as you realize this functionality securely. So I'm only going to tell you about how to build this using quantum information and some crypto. So we'll get to the crypto soon. Okay, so how do we realize secure erasures? Let's again start with a very basic skeleton protocol. Alice is going to sample a random basis, sample a random bit, create the corresponding Weisner state, and send it to Bob. Bob samples some basis, a random basis on his own. He doesn't know what basis Alice used at this point, so best he can do is sample some random basis and measure the state in this basis to get some string y. Now, if Alice's and Bob's basis happened to be the same basis, then Bob recovers x, so y equals x. If their bases are different, and in particular, let's say one is computational, the other is Hadamard, so if they're really these disjoint, then then Bob's string y is uniformly random, Bob's bit y is uniformly random and independent of Alice's input x. Okay, so
binary symmetric channel, probably 1/4.
with probability 1/2.
Oh, well, just because the flip is half the time you're right anyway, so it's 1/4, right? Or binary symmetric.
Okay, possibly. I'm not thinking. Is good to say that again? Like,
So just because y half the time will happen to be the same as x, right? In the
right.
case.
Yes.
So it's 1/4 from
Good.
being wrong.
Right. So if if the bases don't match, then y and x are equal with probability 1/2 and don't match with probability. Yes. So the flip probability is 1/4. Correct. Okay.
In fact, there are even some attacks you can like
Do
get
better.
beyond 75%, right?
Yes.
65%.
Yes, you can get to 85% by not choosing the standard and Hadamard basis, but using intermediate basis. But we're not going to get into that here. So we're going to assume for now that Bob either picks the computational basis or the Hadamard basis and measures. As long as he does that, then you have if the bases match, then transmission occurred. If the bases don't match, then Bob got some random uncorrelated bit. Okay. The issue is that once Bob does this measurement, he can claim that he measures, Alice can send her bases, and now Bob can check whether his basis choice was the same or different. If it was the same, then transmission occurred, he knows x. If it was different, then he has no information about x. So far, while this looks good, the main issue is that Bob can lie. And even a semi-honest Bob can actually lie here, like Yael was saying. So you could have a Bob that does not actually measure and keeps these states as is. And it turns out that in the quantum setting, the definition of semi-honest security is pretty subtle. Again, without getting into the details, the point is that a semi-honest adversary may keep states coherent or without measuring them. Like there's nothing that forces an adversary to actually measure states that they received. So if Bob did not actually measure, but simply just claimed that he did measure, now he's able to recover X with probability 1. Given Alice's basis, he can always measure the state in Alice's basis and get X all the time. So this is like really, really badly broken. So the way to fix this, again, let's go back to the favorite tool, at least for this talk, cut and choose. So instead of claiming that Bob measured, and this was suggested by Crepeau and Killian back in '88, they said, well, Bob can send a proof that he actually measured. So what constitutes a proof of measuring these states? Instead of sending a single state, first of all, let's have Alice send many such Weisner encodings. And Bob, on his end, samples some random basis and obtains a measurement outcome, and will now commit to both his basis choices and the measurement outcome. And this is where crypto comes in. So we need a commitment here in order to force Bob to commit to some choice of basis and measurement outcomes that he obtained. Now, of all of these basis choices and measurement outcomes, Alice will pick a random subset S, let's say of half the bits, half the positions. And Bob is going to reveal or to decommit to both his basis choices and measurement outcomes restricted to the set S. And intuition here is that Alice can check that the decommitted measurements match on every index where Alice's and Bob's basis choices match. So for instance, I have in green here the locations where Alice's and Bob's basis choices match, and in red, the locations where they don't match. I see that that's an unfortunate choice of colors now. Sorry if you can see the difference. But yeah, so the first, second, and the fifth position, they don't match, and the remaining positions, they do match. And Alice can now check within some random subset S whether measurement outcomes match whenever their basis choices match. If that happens, then intuitively, Bob has to have measured most of the remaining positions also in the basis that he declared. And moreover, because at the time of sampling his basis, Bob had no idea what Alice's basis choices were, this means that on the remaining positions, about half the time, Bob did end up measuring in a basis that was different than Alice's basis, and therefore ended up losing information. So intuitively, erasures must have occurred at approximately half of the remaining positions. Again, approximately half, we can't say exactly half because cut and choose has errors. But yeah, that's the rough intuition. Yes, Daniel. Good question. I have a slide about that, so if you still have this question after, please ask again. Yes.
You're committing to classical speed.
Yes, so far this is just a commitment to classical strings. Yes, so I will get to that.
You said that you want that Alice would not know that it arrived to Bob or not.
Alice should not know whether X was transmitted or not,
Yeah.
yes.
But in this case,
She doesn't, because the locations that they're using as their erasure channel are the locations where phi and y were not decommitted. So that's still hidden. So as long as the commitment hides phi and y, Bob's choices of basis on the hidden positions, like on the unopened positions, is hidden. Does that answer your question?
so X is like everything that is outside X. Should think.
So I'm thinking of
Yeah, X, the important X is the thing that are outside of the set S.
I'm trying to get to this slide where, okay, never mind. Yeah, the important part is outside of the set S. You throw away the set S. Yes. Okay. Okay, so what this says is some type of commitment, some definition, which I'll get to in the next slide, implies secure erasures, which implies OT. And so this is great. This is something that we believe you cannot do classically for any reasonable definition of commitments that doesn't like immediately include public key crypto. or trapdoors in it. Okay, so the security of this protocol has actually been quite non-trivial to analyze over the years. 30 years ago, just like QKD, it was believed that you can have commitments, ideal commitments, that are secure against computationally unbounded adversaries. And based on these, there were proofs that this particular protocol is a secure OT protocol. And so quantum MPC was believed to exist based on these types of commitments secure against unbounded adversaries. And this was first proposed by Crepeau and Killian, and there were proofs of security in Mayers and Salvell and Yao's works. And these proofs are correct. So they show that if you have access to an ideal commitment, which has hiding and binding against unbounded adversaries, then OT exists. Years later, it was discovered by Mayers and Low and Chow, well, 2 years after these works, that commitments against unbounded adversaries are actually impossible. So you simply cannot have, even with quantum communication and quantum resources and quantum computation, you simply cannot have commitments secure against unbounded adversaries. So either one of hiding or binding has to be only against computationally bounded adversaries. Yes?
Why was it believed that it doesn't? Oh.
There were even protocols that were proposed. Well,
there was like work with a bug in it. Is that what happened?
yes. Like there were no proofs, but there were claims that this is a secure protocol.
So
And
there
then-
were like unproved claims.
Yes.
That there was claims, so people just said,
Yes, yes.
I'm old enough to spend the summer trying to do that.
to try to do.
Trying to prove that the commitments exist.
Oh, okay.
But Only wrong.
Yep,
Yeah, but a priori it's not obvious, but you know, you can show, well, not show, but claim that it is later proves that it exists unconditionally. For OT, is it obvious that it doesn't exist unconditionally? Right, you kind of said for commitment it's a
Yeah.
secret, but for the actual primitive that you care, is it obvious?
Yes, yes. In particular, OT will imply commitment. So that's one obvious way to see it. But yes, you can have a very simple proof. In retrospect, a very simple proof that commitments against unbounded adversaries are impossible and OT against unbounded adversaries is also.
So it's a simpler proof that commitments. You're saying OT proof is.
Equally simple. Both are very simple proofs in retrospect. Yes. Yes.
Have any idea why they're simple in retrospect and were not simple before? It's kind of hard for me to imagine why they couldn't see it. Of course, like we are steeped in the modern tradition and this, we don't.
I don't know. I don't know.
That's a lesson for students, you know? You see
Good
things,
question.
you know, it's not.
I think it was the definitions, right? Like the definition of what a secure commitment was like not super clear for a long time. Like this is partially what Mark talked about today. Like about breaking binding of like giving two openings. That was not the right way to think about it in the modern setting. But now with like modern definitions,
True. Like I think while that's one reason, I mean, even for the simplest definitions you can come up with, I would say it's now at least fairly simple to show that commitments cannot exist, right? So, even if you're
Also just the really back then was much more buggy. Seriously, most of the proofs in quantum land back then were just wrong.
I wonder if 20 years from now we'll have, you know, machine checked proofs of everything, and then we'll be saying the same thing about this generation.
Yeah, hopefully.
Okay, so all right, so so this is where we were, but turns out that extractable and equivocal commitments, or in other words, commitments satisfying the real ideal definition of security, all used to, are sufficient to obtain OT. And this was shown by Damgaard, Fell, Lunevan, Salvell, and Schaffner. And then I would say a easier proof by Bowman and Fair. Okay, so these are good enough. And moreover, it turns out that any classical commitment can be used to build extractable and equivocal commitments with access to quantum information. And therefore, you can use any one-way function or post-quantum commitment to get OT with access to quantum resources and quantum communication channels and so on. And this was, this was shown in two joint works, Grillo, Lin, Song, and Venkathanathan, and another work of mine with Bartosek, Colangelo, and Ma. And moreover, this construction is black box in the one-way function. So this is something that is, you know, provably impossible with just classical capabilities, but possible now with quantum capabilities.
But again, when you say any classical commitment,
Yes,
you mean any classical commitment with kind of classical definition?
with classical definitions, yes. Okay. This also extends to quantum commitments. Now, a quantum commitment is a way to commit to a classical bit, but using quantum information and quantum communication. And therefore, quantum commitments also imply OT. Now, again, like Fermi was saying, there are many subtleties in defining commitments, especially in a quantum setting where you could commit to a superposition over values and then open to the superposition and so on. So it's important to be careful with the definitions. But I would say, again, at this point, the simplest definitions you can come up with via a sequence of transformations are known to imply OT. I'll talk about those in part 2 a little bit more. But yes.
The GLSV and BCKM, these are using like post-quantum definition, like some binding or collapse binding.
Yes.
So this results that, I guess you're saying any classical, computationally hiding, computationally binding would imply, I guess, computationally extractable, computationally equivocable. And I would guess if one side is statistical, it will be statistical.
Yes, so I'm like hiding something a little bit here, which is, I think technically what we show, at least in BCKM, is that Nauer commitment that you get from one-way functions gives you OT. Now, I'm pretty sure you could apply that to any commitment that satisfies statistical binding and computational hiding, but not the other way around.
Not that.
Yeah, not the other way around. Although again, I believe that this work, Anant, Kian, and UN, it applies to a real ideal definition of quantum commitments. Basically, by now, through various transformations, we know of that these are all equal, like in terms of these all imply each other.
But you're saying, so far
One of them is
on
over.
the other side.
Sorry?
If you want like statistical, I guess, hiding, or to use statistical hiding, from, well, I guess we don't know how to get classical one for one function. I guess it's from collision resistant hash functions. But this result is
So I think Fermi has a work, and there's another work that shows that statistically binding computationally hiding commitments imply statistically binding computationally hiding commitments and vice versa. So that's what I meant by that. Yeah. Okay.
Do you know is that round preserving, or does it have all the linear rounds?
Around non-interactive. You can like generically make all of them non-interactive. Is that right? Yeah.
To make them extractable and equivocal, you probably need stuff.
Yes. So this is vanilla commitment. To get extractable and equivocal, you need space to rewind, for instance.
But do we have like bounds on the round commitments?
Not that I am aware of. Yeah, it's a bit open question. Okay, so this is where things stand in terms of OT. Now, the question then is, since quantum commitments suffice to obtain OT, and maybe you can get quantum commitments without one-way functions. So, and in general, what kind of computational hardness is needed to build quantum commitments? And this is going to be the focus of the second part. So I'm going to get back to this question soon. For now, I'm going to move on to another application of Weisner encodings, certified deletion. So what is the setting here? You have Alice that has a database D, and she wants to store this database on some untrusted server, Bob. And then later on, she wants Bob to actually delete her data and prove to her that he has deleted it. Now, if this encoding is classical, there is no hope of ever achieving any kind of security here. The server could simply stash away many copies of this encoding and then maybe show like that he's deleting one local copy. But there's no way to check that Bob hasn't kept around many copies forever. Now, Broadbent and Islam first noticed that you could use quantum information to delete these encodings in a way that classically is completely impossible. And in particular, if the encoding is quantum, then Alice could issue a request saying, please delete my data. Bob could send back a proof. And, and the no cloning theorem makes it possible to actually provably, to have a proof here such that if the proof verifies, then Alice can rest assured that Bob has no way to recover her data, and has information theoretically deleted this data from his view. So Broadbent and Islam originally imagined this in the context of one-time pad encryptions, where this encoding is a one-time padded encoding, and Alice keeps around like the entire key. And then in a work with Bartosek, we generalized this to a setting of computational encodings, where as long as in quantum polynomial time, Bob is unable to recover the database, or as long as you have hiding from, computational hiding from the encryption scheme that you're using here, then the guarantee is that after deletion, Bob, the server, cannot recover this database even given unbounded amount of time and resources. So it's information theoretically removed from Bob's view as long as the proof that he provided verifies. I hope the setting makes sense. Yes.
Are we requiring the proof to be a classical proof?
It will be a classical proof. Now there's different papers that look at both classical and quantum proofs. For instance, you could just ask Bob to return the entire encoding and test it, and that would be one way to do it. But you can also do this with classical proofs. So in this work with Bartosek, for example, we have classical proofs. Yes.
What's the difference between the 2020 work and
the 2020 work is about one-time pad encodings, specifically, which are already information theoretically secure in some sense. And what it says is, as long as the one-time pad key is hidden from Bob at the time of producing this proof of deletion, once Bob has produced the proof, even if you give them the key, they're not going to be able to recover the database. Whereas the 2023 work generalizes it to computational encodings, where note that this encoding that Bob has, prior to generating the proof, it completely determines Alice's database. So the database is information theoretically actually present in Bob's view prior to generating the certificate. But after he generates the certificate, you can be convinced that it's information theoretically gone from Bob's view. So now Bob can spend forever processing the rest of his view, but it just does not exist.
There's some reason to want to do it computationally and not use the one-time pad.
Good. So for one, you could, with one-time pad, if you wanted to decode it at some point, you would need a huge key. And with computational encryption, we know that you don't need huge keys. That's like the foremost reason.
But in both cases, the server, Alice, I guess, needs to store some key.
Yes, if she wants to decrypt and make use of this encoded data at some point. Note that this has to be an encoding.
Yeah, why does it have to be an encoding?
Because if I give you some data in the clear, then there's no hope to ever ask you to delete it, no matter
if I know what it is.
Yes, if you know what it is.
If it has entropy, then okay, but that's why the encoding.
Yes, that's where the encoding is. Yes, to hide it. So we need some type of hiding in the first place. And what this is saying is if you had computational hiding to begin with, you can convert it into information theoretic hiding given the certificate.
But you design the encoding, right? So it's not like, the way the assumption is stated, if you so in the encoding, you construct as part of your thing. So then what is this assumption?
Good. So it's somewhere in between what you're saying and so in the sense that you can use basically any encryption scheme we show, along with a few like quantum and pieces of quantum information attached.
You have some kind of blood box.
Yeah, compiler.
Strengthening.
Yeah.
I'm a bit confused about the one-time pad. It seems to me that there's not much difference before the deletion and after the deletion. The server cannot.
So the thing is, after deletion, if I give you the key, if I give the server the key, they still cannot recover the data. Whereas pre-deletion, if they had the key, then they simply XOR and recover. Okay. So what does this encoding look like? Let me give you a small flavor. You take any encryption scheme that satisfies CPA security and create these Weissner encodings as before, encrypt the choice of basis. So now you know that by combining these encodings with the choice of basis, you can recover the information string X corresponding to what bits were encoded here. And now use the parity of that string to hide the bit B. So that's what the encoding looks like. And the proof part, yeah.
That's inside the encrypt?
Sorry?
That's the B XOR parity of X
is inside the encrypt. We don't know how to pull it out. We think it should be secure even if you did pull it out. We don't know how to prove it, but it is inside. We can't even prove CPA security for like encrypt theta and then B XOR parity of X is out in the open. We don't know how to prove that this is CPA secure, strangely. So I think it just needs new techniques. Yeah.
If it's a parity, you did some gold reg lemon thing.
Yeah, we still don't know how to prove it. It didn't help with proving security while pulling this out. So yeah, anyway, but you can prove security with the B XOR parity of X inside the encryption. But that's a good question. And yeah, the proof of deletion is simply ask Bob to measure all the qubits in some one fixed basis, like the computational basis or the Hadamard basis. And now check that the measurements actually match Alice's string. So now even here, Alice needs to store the entire string X and the entire string theta in order to check Bob's proof of deletion. Okay, this is not the most ideal. There have been some attempts to increase rate so that you don't need quantum resources that scale with the number of bits you're trying to encrypt. Yeah, but yes.
Is it possible, or maybe that's how you formalize it? The result that I would like in the settings, if you have like any secure message transmission protocol, computationally secure message transmission protocol, instead of the word encrypt, then this would work with some kind of PC framework. Do you have such a result, or you have like a game-based?
So we haven't thought about composability.
But the last thing, security.
It's game-based.
Thing usually really hard. Like these two-stage attackers where your computation, usually composition doesn't work. So you're saying you're not sure if it works.
Not sure if it works, yeah. We do a game-based analysis as long as this satisfies CPA style hiding, the overall scheme satisfies certified deletion security.
Is it meaningful? Because initially I thought you have a result, and this is super cool, but I thought initially you had something even more amazing, that somebody just gives you an encryption of E, whatever way you don't know, and you put some quantum stuff on top of it, and it works.
No, yeah, that would be very cool. I agree, but I don't know how to do it.
Possible or not? Okay. Do you think it might be possible?
If the encryption is fully homomorphic, then I think that it may be possible, but not for arbitrary. I don't know. If it's a quantum fully homomorphic encryption scheme, then I believe we could like add quantum states to it. Okay.
But wait, what is the question? You can just encrypt the ciphertext, right? Using your encryption.
No, I think Evgeny wants to say that like someone gave you an encryption. Now don't use any other encryption schemes. I guess like you don't get to pick what to encrypt. Like someone else picked something and encrypted it. You do some quantum magic on top of this and create a new ciphertext, which can be deleted. I don't see how to do that.
What does it even mean? Like that quantum magic can be another layer.
Not sure.
Let's talk about this. Yeah, I think I get a sense of maybe what you're saying. Let's talk about it. Okay, so the point is that if as long as the proof verifies the bit B that was encrypted here is information theoretically deleted from the server's view, despite the fact that this bit was previously determined by the server. Okay, sorry. So that's all I'm going to say about certified deletion. The next cool application, and this is really cool. There's been a lot of work on this. Is quantum money. Yes.
Maybe like a quick question about the thing. So you stay in the product, you're saying you have a proof.
Yes.
I'm curious, it looks like there is some, are those proofs like very non-black box, or there is like one information theoretic thing that you can prove from each of those applications of Weisler and Turing kind of follow, or you have to like work case by
You
case?
have to work case by case so far. Yeah. Maybe there's like a unified way to prove all these things because the proofs like use similar ingredients. Okay, so quantum money. So quantum money considers a situation where quantum states are used as banknotes that cannot be cloned. So consider a bank that's minting money in the form of a quantum state, sending it to Alice. The guarantee is that Alice cannot create two copies of this banknote and send them across in such a way that both copies will pass some verification test. One simple way, again, to use Weisner encodings to build quantum money is the following. The bank samples some serial number S and then applies a PRF to S. So again, think of this as like the bank has some random mapping between S and some public, between S and some other string Y. And this other string is used to sample both a basis theta and the information string x. And then the bank uses this to create Wisner encodings as before and sends both S and the Wisner encodings as the quantum money state. So S is typically called the serial number of the banknote, and this remaining part is the actual banknote. And the idea is that because these states cannot be cloned, which is again the proof of this is not something that I'm going to talk about in detail at all. It turns out that access to these states, well, one way to think about it is that Alice cannot tell whether she obtained standard or Hadamard basis states based on what we already talked about. And the only way to recover information about these states is by measuring them in the right basis. But she doesn't know what the right basis is, so she has no information. Sorry. Okay, so given these states, it is impossible for Alice to create two copies of the exact same states that would both verify against the serial number S. I did not describe how verification works. Sorry, I think I skipped something on the slide accidentally. The way to verify, given a banknote and a serial number, is that the banknote uses PRF applied to the serial number to compute a description, theta and x, of the state, and then just checks if the state matches this description. Okay? So note that, again, a PRF applied to S with some hidden key that the bank has gives the bank a complete description of this state. And given that description and a copy of the state, the bank can easily check whether the state is correct or not, simply by checking if this is the KED 0 state, if this is the KED plus state, and so on and so forth. Okay? Yes?
I've seen this stated like information theoretically. Like what if you don't use the PRF? What goes wrong there?
It works. The PRF is just a way to compress the key that the bank holds. You could use, instead of a PRF, the bank could create this giant random oracle that maps S to descriptions, every S to some random description. You could use that. Okay, so that's how verification works. And the no cloning, the no cloning theorem basically says that it is impossible for Alice to create two banknotes that verify with larger than some fixed probabilities. Okay, the drawback of this scheme is that only the bank can verify these banknotes. One solution to this, so that anyone is able to verify a given banknote, is to try to obfuscate the bank's verification functionality. So what if the bank gave out an obfuscated program that allowed for testing if a given state was correct? The issue with that is that this obfuscated functionality can actually be used by Alice or any other party to clone arbitrary banknotes. So how does this work? Well, if you have access to the verification oracle and access to some valid banknote, then given the verification oracle, it's possible to actually learn the description of every state in the banknote. How? I have a hint here, which is you can start by substituting the first note with simply the KED 0 state. The first qubit with simply the KED 0 state, and keep the rest of the state as is, and see if the bank likes this and like if this passes verification. If it does, then you know that the first state is KED 0. If it doesn't, then you try with a different state, and you keep repeating this a bunch of times, and you can recover information about each qubit of the state. And this gives, this gives rise to an attack, basically, if you were to reveal any, even in an oracle model, if you were to reveal access to the verification oracle, the scheme would be insecure. Yes?
That you can repeat of the verification.
Yes.
To have some kind of one-time verification, some quantum that once you use it.
Good. So
destroys the state if it's not passed.
Good. Yes. So there's actually attacks that work even in that setting. So you could imagine a bank that destroys the banknote if it fails verification. So like you get to fail verification once. If you fail, then I'm going to alert the police or something. But it turns out that there's something called the Elitzer-Weizmann bomb attack, which allows you to bypass this type of bank. I'm not going to talk about it, but turns out there's still an attack. what I'm interested in more here is this Oracle model, because I want to motivate a setting where verification can be made entirely public. And so, of course, if verification was public, then you can access it as many times as you want.
I think the problem is there is no real one-time program. There's this idea of proof doesn't really exist in the market.
Okay, so to fix this problem, sorry, yes, you have a question.
Oh, is there like a limit on like the length of S? Like, is there a ceiling on how many banknotes a bank can print, for instance?
Exponentially many. So the length of S is like polynomial in the security parameter typically. So the bank can theoretically generate like exponentially. The bank has the capability to pick exponentially serial numbers from an exponential size set. Yes.
If I mean, a kind of set obfuscation thing kind of doesn't work, but if I'm interested in symmetric key solution, it sounds that I just want one-to-many, secret one-to-many, secure against verification oracle. Is there a simple way to fix it without any obfuscation? Also, like secret key primitive with verification oracle. Do we know how to do it simply?
So you mean that
Well, like this,
secure against repeated queries to a verification oracle?
This scheme doesn't work even if you
Yes, exactly, exactly.
So if I, allow you oracle access, so now it presumably I don't need obfuscation.
Yes, I'm going to show you next. So, yes, so do we have a way to create states that can be verified, but where access to the verification oracle is not going to allow you to learn or clone the state? And it turns out that there's a type of highly entangled state. So the states we were just looking at were single qubits, not entangled with each other. Whereas if you use more entangled states, then this can be made to work. The state is what is called a subspace state. So you pick a random subspace, small subspace of f2 to the n, and the dimension of the subspace is like it has n by 2, let's say, vectors. And so you take the span of all of these vectors, that's your subspace, and create a state that is a superposition over all vectors in the subspace. Okay, so this is what is called a subspace state. And it turns out that these can be verified given membership oracles for the subspace and its dual. So if you had an oracle that simply output 1 if you give it a vector in the subspace and 0 otherwise, and also for the dual of the subspace. So the dual of the subspace is the set of, is the span of all vectors that are orthogonal to every vector in the subspace S. If you give access to both of these membership oracles, then you can verify that a state is actually of the right form, that it's a superposition over everything in the subspace. How do you verify? You first run the state through the subspace membership oracle, check if the oracle outputs 1. Now, it could output 1 even given a few of the vectors in the subspace, doesn't have to be everything. So to make sure that you have everything in the subspace, you take a quantum Fourier transform of the state and run it through the dual membership oracle. And this will test if the state is exactly a superposition, a uniform superposition over all vectors in the subspace. Okay? So both tests will pass with probability 1 if and only if your state is of exactly the right. Does this make sense? And this was first, it was first proved, and this type of scheme was first proposed by Aronson and Cristiano, who also proved that a polynomial number of queries to these oracles do not actually reveal the subspace state, and you actually do have unclonability even in the presence of these oracles. And it turns out that this is also obfuscation friendly. So Zandri showed that these oracles can be obfuscated, assuming I/O, giving rise to public key quantum money from assuming post-quantum I/O. Now, there have been many other constructions of public key quantum money. Yes.
You are assuming I/O, but I/O, you don't have I/O that is postponed.
Do under assumptions that may not be as standard, but you do under, I don't know, the circular security of some types of LWE assumptions.
You didn't give us any candidate. It was all.
It comes with the obfuscation workshop.
I think Ayush and Rachel have some recent candidate.
There are candidates that are still out there.
Just not under standard assumptions.
Not under LWE.
I mean, not in my talk,
Not in your talk.
but it's an evolving field. I mean, it's a moving target. There's still attacks and ideas coming out.
Okay, so you're assuming there is an I/O that's post-quantum secure.
Yeah.
Under that assumption,
That is public key quantum money.
You have quantum money. Okay. It's equivalent to it?
Good question. No, actually, there's been at least like some serious efforts to get public key quantum money from LWE directly. They haven't succeeded as far as I know yet. But yeah, maybe that you can get public key quantum money from LWE, but IO turns out to be harder. I don't know.
The secret key quantum money is just one-way functions. It's just a PRM.
Yes. Yes.
And then only for compression. Everything else is a compression.
Yes.
Third bullet, that's do not reveal the subspace state. You mean like
I mean, you cannot clone. Yeah. Okay. So this is all I had to say about quantum money. Let me add that there are other candidates based on knot theory and on group actions. So there's like, this is an exciting evolving field. There are these candidates that I haven't talked about. But yeah, it's cool to try to like solve this problem of building states that can be verified but not cloned even with access to verification or the verification functionality itself. Okay, beyond quantum money, there's been some primitives that are even more powerful that have been introduced. So Xandri introduced quantum lightning, where the idea is that even the mint or the bank cannot create two banknotes with the same serial number. In quantum money, it's just other parties that cannot create, that cannot clone banknotes. Here, even the bank cannot, even at the time of generation, generate two banknotes with the same serial number. There's one-shot signatures, which are even stronger than lightning, where you can think of the lightning state as a signing key, which can sign one single message and then provably self-destructs after signing this one message. I want to say that Shmueli and Xandri have a recent, very exciting construction of both these primitives from indistinguishability obfuscation. Previously, it was open to construct them even in an Oracle model. So you should ask Omri about it. Okay. All right, some more applications. I think this is the last one. So generating true randomness. Consider a setting where you have Alice and Bob. Alice, again, creates these Weisner encodings, sends them all to Bob, then sends some random basis to Bob, should be different from her initial basis, and asks Bob to measure them, measure these states, and Bob measures them and generates the outcome. Here, think of Alice as being honest and Bob as being potentially malicious. What Alice can do at the end is check that the open measurements, the measurements opened by Bob, match her string X when the bases match. And now if the bases don't match, you have confidence that on positions where bases did not match, there is high entropy in Bob's measurement outcomes. So these 1, 0, 0, the red parts of the string where Alice's and Bob's bases do not match should have high entropy. Now, at first, it may seem like, why are we even doing this? They're both quantum machines. Why not just prepare something, measure, like prepare the plus state, measure in the standard basis, get randomness? Well, this becomes interesting if you think of Alice as being classical only and Bob as being a quantum machine. So, okay, at first, this may not make a whole lot of sense because we're having Alice send a bunch of states to Bob. How can Alice do this if she's just classical? And this is where this primitive called oblivious state preparation that I mentioned briefly in the beginning helps. So there is a protocol, a cryptographic protocol that we can call interactive oblivious state preparation that allows Alice to end up with some number of basis and string information, and for Bob to end up with the corresponding Weisner encodings. So this is essentially simulating the part of the previous protocol where Alice was sending over these states to Bob. Instead of Alice preparing and sending the states, this is a protocol between a classical Alice now and a quantum Bob, where quantum Bob will end up with the Weisner encodings and Alice ends up with their classical description. Okay? And now they can run the same protocol. Yes, yes, yes. Yes, good. So what does oblivious mean? So let me answer that actually right away. So oblivious state preparation, the O in OSP is for oblivious. What this means is Bob doesn't actually learn what bases are being used to prepare the states that he ends up with. We should think of this as, again, Bob ends up with these states but doesn't know what they are. Formally, the only security requirement is theta is hidden from Bob in a CPA hiding sense. Okay. Now let's imagine running the same protocol as before. We send a random basis phi. Bob measures, sends the measurement outcome back. Alice, who has information about what these states were, she has X. She'll check that X and Y match when the basis choices match. And if this check passes, then measurements on the remaining indices have high entropy. So that you can think of this as a way to get certified randomness from a quantum computer by like a classical device interacting. Okay? Yes?
So here you kind of arbitrarily or not say like, pick like another basis completely random. If I really want to kind of extract the literature to extract close to what I can, I would just basically only choosing security parameter things.
Yes, I'm not trying to be efficient here at all. But yes, I think it should. Yes. Yes, but I'm not trying to extract the maximum randomness you can, etc. Just saying, yeah.
X is not hidden?
Yeah, formally we don't require that X is hidden, but just theta being hidden actually implies that X is hidden. But if you try to define the simplest possible primitive, you can just require correctness, which says Alice ends up with the description of these Weisner encodings, Bob ends up with the states themselves, and the basis choice theta is hidden from Bob.
Sorry, what is the difference between OSP and remote state preparation?
Great, I will get to that in 2 slides. Okay, so this was just a sneak peek into oblivious state preparation. Let me actually now tell you formally what this is. There's a classical sender and a quantum receiver. This is an interactive protocol that gives the classical sender the description of a string and some bases, and has the quantum receiver end up with the corresponding Weisner encoding states. And the security property is just that the basis choice theta is hidden from the receiver. Now, many of you may have heard of what is called remote state preparation instead of oblivious. And the difference is that there is no verifiability property required by oblivious state preparation. So in other words, a malicious receiver could end up with some completely arbitrary state that's not the right Weisner encoding. We don't care. The only security requirement is that the basis choice theta is hidden from the receiver. So it's only hiding. On the other hand, remote state preparation requires that the sender should be able to verify at the end that the receiver prepared the right state. And that turns out to be tricky. We don't know, for example, how to get remote state preparation from oblivious state preparation, except with some error. Like you can do cut and choose type tricks, but they leave you with some error.
So remote state preparation implies oblivious state?
Yes, but not vice versa, exactly. Yeah. Remote state preparation is a stronger definition, where in addition to hiding, you require that the receiver end up with the right state. Okay, yes.
Does the sender get to choose theta and S, or is it just given to them?
Right, good. So the way I've written it, it's given to them, but they can reorient. So like in OT, you can choose inputs and reorient the protocol. You can do a similar thing here. So in other words, you can very easily convert this into a protocol where the sender gets to choose theta. Yes?
I don't think I understand the difference. So you're saying OSP does not
does not have a verifiability requirement, or I guess it doesn't have a correctness requirement against malicious receiver. So a malicious receiver could end up with some completely different state. We don't care. So this primitive, like this primitive was abstracted out in this recent work with James Bartosek. And we showed that you can construct it from trapdoor claw-free functions using techniques that are very similar to and inspired by this entire line of work, starting with Mahadev's works. So we use trapdoor claw-free functions. What is this? This is a keyed family of 2-to-1 functions where every image has 2 pre-images. Well, not, yeah, you can see in the diagram what I mean. And it's easy to invert given a trapdoor.
And by the way, there already exist remote state preparation protocols for Weisner encodings, right?
Yes, there with error.
With the poly error.
Yes.
And that's what you're trying to do.
Yes, yes, yes. Okay. All right, so constructing oblivious state preparation, it follows basically a very similar template, and this is just abstracting out prior work in a different way, essentially. So the classical client samples a secret key and public key for a 2-to-1 trapdoor claw-free function family. The server uses this to sample a claw state, which is a pre-image over superposition over both pre-images of some string y. The classical client then samples a random z such that, well, it's able to recover both pre-images of y, and using them, it samples a random z that has inner product 0 with the first pre-image and inner product 1 with the second pre-image. It sends this to the receiver. So this z acts as a way for the receiver to isolate which one out of 2 pre-images it has in its superposition. And then the client also samples 2 random strings r0, r1, sends them across. The server, as this claw state, its goal is to get from the claw state to a state of the form x0, comma, x0.r0 plus x1, comma, x1.r1. And turns out it can use the z to isolate like 0 against x0, 1 against x1. And now, controlled on 0 versus 1, it can compute a product with r0 versus r1 and get this state. This is not very important. Basically, elementary quantum operations will get you from x0 plus x1 to x0, comma, x0 plus r0 plus x1, comma, x1.r1. And now, if the server measures the first register in the Hadamard basis to obtain a string d and sends it across, and it outputs its last register, then this basically gives OSP for Weissner encodings. So let me repeat that. The server is going to measure the first n qubits in the Hadamard basis, and then just output the last register that it has as its Weissner state. And using the Hadamard basis measurement d, the client is able to recover a description of the Weissner state that the server ended up with. Yes.
So is that cat x0, cat x0 dot r0?
Yes.
Which is just 0.
Inner product.
Oh, no, that's a different. Okay, good. My confusion.
Okay. Yeah, r0, r1 are 2 random strings.
How do you like unconfuse delete the 0 on the 1?
Again, using the z.
You say how to sample the z.
Sorry?
You say how to sample that z.
Just at random, such that it satisfies z times x. The inner product of z with x0 should be 0, and the inner product of z with x1 should be 0.
Because you have a secret key.
No, yeah.
Oh, you don't. You know x0 and x1 because you have the secrets. There's a client that's sampling z. Yes. Okay. All right. So all that this is saying is you can use any trapdoor claw-free function. We're assuming idealized, but you can also use noisy variants of these functions to try to have to build a protocol where the server ends up with a state and where the client has enough information to find out what this state is. Let me tell you how now. So note that the server ends up first with a state that looks like x0, comma, inner product of x0 and r0, plus x1, comma, inner product of x1 and r1.
No, wait. Hold
Yes.
on. It doesn't have that because you did Hadamard and measure.
Oh, before that, I'm just explaining how the Hadamard is going to affect this state.
Okay.
Yes. Pre-Hadamard, the server has the state. Now I'm claiming that if you Hadamard and measure the first register, send it across, keep the last register, then this is it. This is end of protocol. So now let me explain this claim. So that's the state that the server has, x0, comma, x0.r0 plus x1, comma, x1.r1. Let's say that x0.r0 equals x1.r1. And again, note that the client has all this information. It knows x0, x1, r0, r1. So it knows whether they're equal or not. Let's say that they are equal, and let's say that this is equal to s. Then if you did a Hadamard transform on the first n qubits, you basically just have the state x0 plus x1 tensor with s. And then you get a state that looks like this. You can just ignore this state basically, because you know that the last qubit is simply ket s. So the receiver outputs the state ket s, which is the standard basis state, which is 0 if s equals 0, 1 if s equals 1. And the sender also knows what this state is. So it knows if x0.r0 equals x1.r1. If they are equal, it knows that the receiver ended up with the standard basis state, and it knows the value of the state, which is simply x0.r0. Right? So if they are equal, then the receiver outputs a standard basis state, and the sender knows exactly what state, which is what we wanted. Okay? Now, let's say that they're not equal. Now, if you look at the Hadamard transform on the first 10 qubits of the state, you can write down the transform, but this is what the state looks like. You have ket D on the first 10 qubits, along with the state where the relative phase between x0 r0 and x1 r1 is -1 to the x0 dot d XORed x1 dot d. Okay. So what that means, because we know x0 r0 and x1 r1 are different, this is either the plus state or the minus state, depending on what this relative phase is. And the sender knows exactly what this relative phase is, given D. Okay. So that's what the relative phase is, given D. Given D, it's easy to compute. And so the sender outputs a description of the state. The receiver outputs the state itself. So that just completes a description of how you can get oblivious state preparation from 2 to 1 Traplow-Claw-free functions. Let me just point out why this should be secure. Yes.
We should take a break.
Okay.
Right,
Let me just, this is like second last slide. So, okay. So if the receiver is able to predict x0.r0 XORed with x1.r1, which is the value of theta, which is the thing we're trying to hide, then via simple goal-right-Levin argument, you can use the receiver to extract x0 concatenated with x1. So you find the claw, breaks the Traplow-Claw-free function. Okay, I should also just mention that the fact that theta is hidden from the receiver basically can be converted, and this is a very informal statement, but can be converted into an argument that the state that the receiver ends up with here is unclonable. And so you can use this to get many applications. So for example, proofs of quantumness, classical delegation of computation, in fact, even OT. So just this primitive gives OT, public key encryption if you have it in the 2-round setting, quantum money with classical communication. So I won't name them all, but there's a bunch of applications that you can get simply by taking an information theoretic protocol where you have Weisner encodings being sent around and replacing it with this abstraction, which generates the encodings between a classical client and a quantum server. It's not, the proof is not as simple as this, but this is a good starting point. Okay, so that's it. Thank you.
So we take, I guess, to be half an hour, should we take, how, this next one is going to be shorter?
Similar, it was similar number of slides, but I can try to make it shorter.
Yeah, worse. Okay, let's take, I guess, the 30-minute break that was scheduled, and then we'll just.
Yeah, shorten it.
Uphill.